Hi everyone, welcome to this new lecture of fluid mechanics. In this lecture, we'll discuss a new topic regarding the power absorbed in the viscous flow. So in viscous flow, the power is absorbed due to the resistance to motion which is caused by the fluid internal motion. Okay, when the fluid is moving or fluid is in the motion, due to the internal friction, and the power is going to be absorbed, and that is happening due to the viscosity of the fluid. Okay, so if you know this concept of this, like why this lubrication is required in the machine parts. Okay, for lubrication of the machine parts, if you know, we used to use a oil. Okay, for lubrication any kind of machine parts, we used to use oil in our machine parts, in our vehicles, everywhere we used to use engine oil. We used to use on our vehicles to having a better lubrication. So the flow of oil in the bearing, that is, you can say the best example of this viscous flow. Okay, when the flow of oil flow, you can say in the bearing, oil flow in the bearing, we can consider a best example of this viscous flow. Okay, if suppose a highly viscous flow will be considered, or that is going to be used for the lubrication, then it will be offer a great resistance. If you use a high viscosity fluid, then the resistance will be very high. High viscous fluid, if you consider, then it will be give a more resistance, and more power is going to be lost. Okay, more power is going to be lost in that. But if you consider a light liquid, okay, which is having less viscous, in the less viscosity, less viscous fluid. Okay, then in that, the film which is required between the rotating parts. Okay, the rotating parts between the and the stationary, any kind of metal, suppose, then the surface will be not possible in that. Okay, so the wear and tear between these two surfaces takes place. That means a minimum viscous fluid required, which will be the optimized for a better movement, better rotation of this. So here I have taken a consideration, bearing is there and a shaft is there. I'll discuss that one. So a perfect oil need to be selected. That means a perfect amount of viscous oil need to be selected, which will be used not either high viscous or not less viscous. So that need to be considered. And to overcome this kind of problem, what is the power is going to be absorbed? Okay, so there are few cases are there. So in that, first one is the viscous resistance of journal bearing. This is one type, and similarly two more are there. This is first one, viscous resistance of journal bearing. Similarly, viscous resistance of footstep bearing is there, viscous resistance of collar bearing is there. So these are the types of this power absorbed in viscous flow. So today we'll discuss about only this concept, the viscous resistance of journal bearing. For this I have taken this one. So here it is. If you see, okay, if I draw, there is a pipe what we have considered here. So this is the circular part of this, and this is the shaft. Actually, you can say the shaft, not pipe. So this is the shaft which is going to be rotated, and this is the bearing part is there. So bearing part, in between this shaft and the bearing part, we have a liquid is there, or oil is present, this one. So the oil we can give it here, this middle of this. Okay, so that the movement of this shaft will be very smooth. Okay, and the shaft is having a diameter of D, and you can say this radius R is there, and the distance or the thickness between this journal and this, you can say this bearing, this is bearing part is there, and this is our shaft is there. Suppose between this shaft and the bearing, we have oil film is there, and oil film is having a thickness of T, and the length of this part we have considered with the length of L. So this is the all total of this. So we have considered a shaft which is having a diameter D. We can say diameter D, which is rotating in a journal bearing. Now, as I told you, the clearance between these two parts is T, that will consider. Now we are going to derive this equation for that. So let's see what are terms are there. Now when this journal bearing is going to rotate, that means N, the speed of the shaft in RPM. So these things I hope you know this terminology, speed in RPM, and T is the thickness of the oil film, we can say, and let me write this, thickness of the oil film, and the length is the L equal to length of the shaft, you can consider, or oil film, we can say. Shaft we can say this is long, more length is there, only what is the oil film length is there, based on that we have taken this length. So length of the oil film. Okay, now when it is going to be rotated, or when it's going to be rotated, this shaft, so there we need to consider the angular speed. So first things, let's identify the angular speed of the shaft. The angular speed of the shaft, which is represented by omega, we know this, and this will be written as 2 pi n by 60. 2 pi n by 60. This is the angular speed, okay, of the shaft. Now we need to find out, or we can say, now next we can write the tangential speed or the linear speed, we can say the tangential speed of the shaft. We can write what is the formula can be written for this angular speed or linear speed for that. Now what is the normal speed, angular speed is there into the radius, so that is nothing but we can write omega into the radius r, at what it is rotating. So this one omega we can write 2 pi n, this is r by 60. So this r we can write also d by 2, diameter by 2, so we can write this pi dn by 60. Okay, r place I have written, so here you can write r equal to d by 2. This is the next terminology. Next we can write tangential speed I have completed. Now we'll go for the shear stress. We'll calculate the shear stress in the oil. Shear stress, because the oil is there, so what is the resistance is offering here. So this is shear stress in the oil. We know the formula, tau equal to mu into del u by del y, or du by dy. Actually this is as per the Newton's law of viscosity. So we know this formula, so just put this value, put this formula here, as per the Newton's law of viscosity we can write. So here if you see the du by dy is nothing but what is the change in velocity, and with respect to the thickness or distance, we can say. So distance is nothing but already it is there, already t is there, so there is no change in that. But velocity we can say, we can change in velocity only v, only one velocity will be there, initial velocity, there is no final velocity. So that for that we can write this is 0, and thickness t we can consider. This is a very small one, so there is no changes, or no, there is no distance between, or difference between this thickness will be there. So we can consider this v minus e. So we already got this value, so we can write v by t. V by t is nothing but already we got now here tangential speed. So this is v, we can mark it. So this one we can write pi d n by 60 into t. This is what? Now this is the value of du by dy. Now just put this value in this equation, shear stress equation. What is that equation? Now we know that tau equal to mu into du by dy. So just multiply this pi dn by 60 t. Now this is shear stress. What is the next step for that? Now we are going to calculate again the shear force. So shear force is what? Now we know the shear stress equal to shear force by area. Now shear force equal to, we can write shear stress into area. So that is nothing but tau into area. Area of the what? Area of the surface of the shaft. This one, the surface of the shaft. Okay. So this one we can write tau, or in the place of tau we can write this value. Which one? The tau value what we got here. That is pi mu pi dn by 60t. This is 60. Okay. And what is the area value? Now area equal to nothing but pi dl. Pi dl, the circumference of that, or is the area of that shaft, you can say. Now if you just multiply this one, what you are going to get? Now mu, 2 pi's are there, so pi square d square, and this is L n by 60 t. So this is shear force. So why we are calculating the shear force? Now finally we need to calculate the power. So in the power we need required one term is the T, 2 pi n t by 60 torque. So for calculating the torque we require this shear force. So next step is, we can say the torque required for this resistance to overcome the viscous resistance. So what is the torque required? Now T equal to, we know that what is the viscous resistance is there in that, into d by 2. So viscous resistance is nothing but what is the shear force is there. So shear force what we got here, mu pi square d square n into L divided by 60t into R. Actually R in the sense here we can write d by 2 directly. So if you write this, what we are going to get? Now mu pi square dq n L by 120 t. Okay. Now this is torque required. Okay, what the torque required to overcome the viscous resistance. Okay, so this is in terms of shear force into what is the force into radius. So force in the sense that is shear force what we got. Now next thing is, final thing we require the power absorbed in overcoming the viscous resistance. We can write the viscous resistance. Okay, now this one we can write what? Now power P equal to, we know that the formula 2 pi nt by 60. So already we got this value, T value. So just write down 2 pi n by 60 into T value is nothing but mu pi square dq nl by 120 t. So 2 you can cancel, you can write 60. So what you are going to get here? Now mu pi q, pi square into pi q, and here already dq is there. Now here n we are going to get 2 times, so n square into L, and divided by here you will get 60 into here another 160 is there, or we can just multiply it, 3600 will come. So this is the power absorbed, and this one we need to write the unit of watt. Okay, so this is the power absorbed in overcoming the viscous resistance. Now if you see from the starting what we discussed here, as I told, we have 3 types are there. So out of 3 types, this is one type is there. Now viscous resistance of journal bearing. So journal bearing in the sense, so as I told, this is the bearing part is there, and this one, actually this is the diameter of this bearing part, and this is the diameter of this shaft actually, and in between these two we have what, oil film is there. So to overcome the resistance between this, or to a smooth flow of that. So here we want to identify, or we have to identify what is the power is going to be absorbed by this. Okay, so because when there is a liquid fluid flow will be there, there is a internal, due to the internal friction, there is a more heat is going to be created here. Okay, so for that, what are the things I have considered? N, T, L, and then after that I have calculated the angular speed of this shaft, which is omega 2 pi n by 60. Then tangential speed of the shaft, that is nothing but V equal to omega into R. So next, shear stress, we know the Newton's law of viscosity, that is pi tau equal to mu into du by dy. And from there again shear force. So first, second, third, then shear force. Shear force, we can write shear stress into area. Next is torque. This is shear force. Then we came for torque here. This is the fifth one. And finally, the sixth one, that is power required. So the formula is 2 pi nt by 60, power required. So here, if you see, these are the constant terms are there, 2 pi n by 60. The torque term is, again, we need to identify. Okay, so the torque again, to identify this one, shear force into the radius, what is there. So again, we need to calculate the shear force. If you go in the backside also, same we are going to get. So I hope you understand this concept of this. If you're having any kind of doubt or query regarding this, you can give a comment on the comment box. Thank you all.